Hello, how are you doing? We'll start in a couple minutes, so let's take a look at the lab. Hi, everyone. We'll start in about 2 minutes, so let's take a look at your lab in Canvas. We'll go over random number generator today. I'll go ahead and share screen. Okay, so we'll start in a minute. You can download the lab and take a look at the code. We'll address some of the criteria, and then we'll start in about a minute or so. So this is going to be our last lab in the LC-3 series. Next week, we'll still have 2 more chapters to cover. So we will have a lecture portion. For the lab, I'm thinking on Thursday, we can look at final review questions, and then I'll do additional review if it's needed, if we run out of time. That way, if we cover everything by week 12, I can give you 13 and on to work on your project. Okay. So after next week, if we get everything taken care of, you still have a quiz, I think 1 more quiz. Okay, so let's get started. It is 6 o'clock. We are going to go over lab 11 today, which is going to be random number generator. Okay, you can find this on Canvas. I also put the image for the code there. So in this week, similar to last week, we are going to work with an equation. But in this one, we are going to implement a stack. So let's take a look at the criteria for our lab. Okay. I forgot to turn on my, 1 second, let me get the live transcript. So. Okay, so in this lab, we are going to make a program that's going to generate random numbers, and we'll talk about randomization shortly. We are going to use the LCRNG, which is the linear congruential random number generator. Our input is going to be in the range of 1 to 32,766 as integers. They are going to be found at the location hex 3100. Now, when it executes, it needs to generate 20 numbers, and in the interval between 1 to 2 to the power of the 15. Okay, so when it is generated, it needs to display on the console. So when we run the program, you don't have to set any input before you run. You simply run the program and look at your console, right? And I want you to take a look at it and then run it again to see if it's actually truly random. Okay, so let's look over the equation. So for the equation, we have x of n is going to be a times x of n minus 1 plus c mod m. And so when you look at this equation already, you should know that, yes, we are implementing multiplication. We're going to have to implement division. Can you reuse recursion in this? You sure can, right? So we are going to take the constant a and we're going to multiply it to x of n minus 1. And we're going to take the constant c and we're going to apply that with the mod or modulus of m, and they are integers. So for a truly random program, it would have it would use the environment to seed, right? So that means that the seed value would be different every single time. Now, a pseudo-random program, that means that it is a program that looks like it's producing random numbers, but it is not truly random. That it usually seed at the same value. So in the case, if we seed at 0 every single time, our program is going to generate numbers that looks like it's random, but it is not truly random. And that makes that program a pseudo, right, random program. And if you have taken CIS11 with me, we have gone through at least 1 week talking about this, right? So keep that in mind on when you generate the random numbers in this particular lab, okay? So if we're given the seed at hex 0, we would generate a random number sequence, would be x of 1, x of 2, x of 3, and so on. So therefore, we would have x of I in the range of 0 to m of the negative 1 or m minus 1. So eventually, the sequence would then repeat itself. So in the case where if we are seeding at 0, the next time we run the program, it should be producing the same set of numbers. So therefore, it is not truly random. Okay? So keep that in mind. Now, in this program, when you look at the equation, you should know that we are implementing 2 functions or 2 subroutines, like the earlier lab. And we are going to break down our equation to small pieces so that way we can implement that in our assembly program. So for the intermediate operations, your x of n might cause overflow. And so in the case of c is 0, we would need to implement the method to avoid overflow. And so that method would require us to implement the criteria as you would see below the equation there. Okay. Now, in this method, we can say that, yes, this equation can be applied to recurrence or recursive functions. And so when we multiply the x, we would represent that in a fashion where we would apply x to the relation of n and how that would be x would be translated to q and r. So as you can see here, it says a of x, right, mod m is going to be a times x mod q minus r times x divided by q. If x is greater or equal to 0. So anytime that you deal with 0 and positive number, right, we have to implement the first condition here, this part, okay? So that is simple because when you see this, you know that we're branching with 0 positive, right, to be applying this. That means that we have to make sure that we have the label for each one, and then we would then implement that into our program. Now, if it is not in this criteria, in this condition, if it is not greater or equal to 0, then how we represent this would be A times X mod Q minus R multiplied by X divided by Q plus M. Okay, so the difference between this and this is that if it is not greater or equal to 0, then we have to add the M. Okay, now what is Q, you would ask, right? Q is going to be M divided by A, and R is going to be M mod A. Okay, so now to really ensure the no overflow, I think we did one lab where we talked about overflow and how we would use the next location or the next word to store anything that would be overflowing. So here, to implement no overflow, we would need to perform the multiplier as A, and the modulus of M has to be in here. So that will be 0 is less than or equal to R, and R is less than Q. And when you use comparison operator in assembly, like LC-3, you have to think about how you can apply, right, subtraction to really check the value, whether it's going to be greater or less than. Okay, so some point in the program, we have to think about how we would do the comparison there. So for Schrage's method, we would use A, we're going to initialize that at 7 because A is a constant. Okay, so we're gonna have it as 7. So initialize it at 7. M, because we're gonna go to the max of the scope, which is close to the max, I'm saying 32,767. It is gonna be 1 less, right? We won't reach 32,777. We're gonna have it 2 to the 15 minus 1, so it's gonna be 1 less. Okay, so that would represent the M. That's where we initialize it. Then your X, that's gonna be 10. And so for Q, we're gonna have Q is gonna be M divided by A. So once we bring in those values, then we can operate the division. So you would have to have a subroutine and jump to that, right? And then for R, we are gonna have R is M mod A. So again, since we're using modulus, we are gonna apply the division again. So division operation for both of those. Then after that, we would have a for loop, and we are generating number from the first number to the 20th number. So we have to loop through each one. So it's gonna generate one by one, and it could be multiple digits. Just keep that in mind. So we would have a loop for 1 to 20. We're gonna do X is gonna be the equation, right? X is gonna be A times X mod Q minus R times X divided by Q. And then we would have the control statement or the condition. If X is less than 0, then X is gonna be X plus M. And then we're gonna output X, okay? So this, using Schrage's method, we would then have 20 random numbers, okay? And we want to be able to control overflow using this, and this is why we have to apply the condition as would be stated here, okay? All right, any question? Okay, so the next part, it's gonna go over how we can represent the larger values, like your 32,767. So what you would have is, it's gonna be, because it is large, right? We need to make it where it would fit into our word size. So then we would need to use the value for M to produce the maximum non-repeating sequence of integers in the range of 1 to 2 to the 15th power minus 2. And so when you were generating the sequence, right, it's going to give us what looks like random. So here it says that of the random numbers, one can choose A is going to be 7, and we're going to see for x of 0 should never be at 0. It should be any number between 1 to 2 to the 15 minus 2. So ideally, we want to seed it, right, at a different value every single time. That will make it truly random. But if you seed it at 0, right, you're going to see that it's going to produce the same thing over and over again. So coming back to the equation itself, right, how we would be able to apply this, the overall look of the program, so they can give you little snippets here. So when we do the out command, that's going to be your trap with vector 21. And as you learn in all the other labs that we have output on console, right, it is ASCII character that we're displaying. And so when you're using the out, you're able to see the value on console, but it is an ASCII character. So that would mean that it is the least significant bits in the register 0, so that way it can take that value and be able to show it. Okay, so here, what they show you here is that when you display the decimal and digit, they're using the register 3, which happens to be negative. So if I have negative value, if I want to make it a positive value, right, I would then, or if I have a positive value, if I want to make it negative, I would negate it, okay, where I would do the 2's complement. So that way we make it sign, right? And then what we're going to do is we're going to load, right, 0 with the label, and then we're going to out it. Okay, just like this. And then to really output the minus sign, we have to make sure that that symbol gets converted so that shows is the negative value. Then after that, we're going to output the digits. Okay, so if you want to show like -10, for example, you have to show the negation first because that's in decimal value. So we want to show the negative. Then we are going to load register 0 again. And here we have a label called offset. And offset actually has the output digit. So it's going to go to the location of the label and then be able to output that. And so after that, we're going to add register 0 with register 3 because that's combined, right? And then we're going to out. Okay. So here they show you that this is just, and again, right, this is just little small pieces so you can see. So for the minus, we would do the fill with hex 2D, okay? And that's equivalent to the minus sign in ASCII. And if you're not sure, go look at the offset on your ASCII table. Then for the offset, that will be the, remember we talked about the hex is 30 offset. And then if you're using decimal, that's 48, which, you know, you have to, so since we're using hex, that's easy. We can fill it with the hex 30. So ultimately we want to convert it so that way it shows your value accordingly. Otherwise, it won't be able to show the accurate value, right? So if you're just going to out it as it is, it's not, you have to convert it. So you have to offset it based on the difference between 0, right? Between the hex and the ASCII value for 0. Any question? Okay, so here it tells you that when you output decimal digits of one number at a time, okay, so if I have 3 digits, I gotta make sure that it shows, right, 3 times, okay? So that means that we can obtain the digits by successfully applying mod 10 on the number and truncation. So until we obtain a 0. Why am I doing that? Because it is a decimal value and it is a base 10. So we have to do a mod 10. So in the case where if we want to represent the digit, because when you're looking at 3 digits, it's actually, the single unit, the 10th unit, and then your 100th unit, right? So here they show you an example. If your number, right, output is hex 219, that's equivalent to 537. And so what we want to do is we want to apply the procedure where the 7, right, is the farthest, which is your least significant value, is going to be first. Okay, then the 3 and then the 5. So it is in reverse. Thus, we have to output in the reverse order on how they're generated. Okay, so it's going to generate the 7 first, right? The 3 and the 5. So we have to show it in reverse. Okay. Then the purpose of this is to really implement push pop, because when you push in, right, you have to push 7 in first because it's the least significant bit. It's the most, right? Then you're going to push the 3, then you're going to push the 5. Okay, so the 5 is going to go in last and it's going to be the first to pop. Okay, so last in, first out. Now here it shows you how you can implement for the output with stack. So on the left, that's going to be your n, which is the remaining value. We would have the sign is going to be 1, because remember that in binary, right, that 1 indicate that it is a sign or a negative value, right? We talked about that since week 1. So when you have a negative value, if we implement if n is less than 0, then we're going to sign. And we saw this in the prior lab, right? The sign is going to be negative. And so that means that we are going to represent the left is going to be negative n. If it is a 0, then your digit is going to be 0. We're going to push it. So because it is 0 or positive value, right? So in the case of 0, then your n is going to be 0. We're going to push the digit. If the left side is not 0, so while left is not 0, we're going to take the digit. So anything like 1, 2, 3, 4, 5, we're going to take the digit and we're going to mod it by 10. Okay? So on your left digit, we're going to make it a 10th digit. So we're going to mod it by 10 and we're going to push it. So your left is going to be left divided by 10. If the sign is less than 0, then we're going to output the negative symbol. Okay. Then we got to do the gauge for our stack. So we're going to have a register that we're going to meter the stack. If it is not empty, so how do I know if it's not empty? If it's 0, right? Is empty. If it's not empty, it will contain some kind of value. Then what we're going to do is we're going to pop the digit. And we talked about this before, where it uses the bit to indicate whether, something is there or not. So we want to check if something is there. If something is there, then we're going to pop. If something is not there, if it is empty, right, then we're not going to pop. Okay. So if we pop, we're going to then output the digit. So you should have a way to really control, right, what is push and the conditions on what is push as digits onto the stack. And then we're going to take what's on the stack and we're going to output. And remember that when we push it onto the stack, it is in the reverse order of how you read the number. It's going to be from right to left instead of left to right. Any question? Okay, so now here, right, It talks about the stack. I think we spent a couple of weeks on this. So there are 3 things that are happening in our program that are crucial to the stack. We're going to do a push, right, for the values that we want to output. We want to pop it right before we output. And we want to use is empty to gauge to see if your stack is empty or not. Okay. So now when we push, we're going to put it on the register 0 on the stack. Okay. Then when we pop, we're going to pop it from the top of the stack in the register 0. So they already give you the hints there. And then for is empty, it's going to return 1. That's how we're able to check. Okay, in register 0. So that's where we need to check the value, right? If the stack is empty, it's going to return 1. And 0 if the stack is not empty. So that's easy. We can branch to 0. We can branch to positive for that, right? Okay, so then for our register 6, remember that this is the practice. That's our little meter for our stack. That's going to be pointing to the top of the stack. Okay. So register 6 should be initialized at hex 4000 because that's the location of storage where you want your stack to be. That's the base of your stack. And it is not to be overwritten while you're using the stack. For your register 7, this is going to be used to store the return address. We talked about this when we talked about jump to subroutine and unconditional jump. So when you are using this, that's going to be used to calling the subroutine. Okay. Now, always is empty should be called before preceding the stop, right? The pop. So what we want is we want to check the stack and before we actual pop it. Okay. And as we pop it, we're going to output. So check whether the stack is empty before we pop. So if it's empty, pop doesn't occur. So, you know, with that, we would have the if conditions there. So we would branch for that, right? Just like what it talked about right here. Okay, simply look at the values. So the structure of that would look like this. So you have your program happening up here. So in your program, right, you need to load register 6. You need to also jump to subroutine. So there should be subroutine for push and pop. And I will look for this on your project on how you implement your stack. Okay. So for your base, because your stack base, that's at this location, so hex 4000. Since you're going to have the functions for push or pop for the subroutine, you have to define it. And here they already give you the main components of it. So you just have to take this, like this piece right here, and then add it to the program, and then make sure that everything works with the push and the pop mechanism. So in order to move to the top, to move the stack up, right, we're going to subtract 1 from R6. So we're going to add R6 with the -1. Then we're going to store that to register 0. So store register 0 there, return. Then if when we pop, because we store and push, pop, we're going to go the opposite. So we're going to load, right? So you do the opposite. So you're going to load, right, register 0. And that's going to give you the top of the stack because R6, that's our little meter, our gauge for our stack. Then as we pop, we're going to add +1 to R6 because when we push, we subtract. Remember, we grow downward, right? So when you move up, you subtract, you're going to move it back down. So you add. Then you're going to return. Then we're going to have to check if it's empty or not. So when you send it to is empty, right, we're going to load label empty to register 0. And empty is going to be filled with hex 4000. That's your base. Or I'm sorry, negative hex 4000. And then, so here we are going to take register 0 and we're going to add it with register 6. Okay, and put it back on register 0. Then we're going to branch. Okay, so if it is empty, right, if it is, then we're going to send it here. So we check for 0. Remember that section we talked about, return 1, right? Or it would be 0. So this is where we're going to check. So if register is 0 is 0, then the stack is not empty, right? Then you can pop. But if it is empty, if it is equal to 0, then you're not going to pop. Okay. So when we add the 0 here, right, we're going to return. Okay. Just think about like how you write your C++ program, right? The certain part in your function, you're going to return 1, you return 0. So return 0 in this case for us, right, that would be if it is 0, then it's not empty. Then we can go to pop. Okay. For when it is 0, then I'm sorry, when it has the 1, then it is empty. We're not going to pop. Okay, then we're going to return. Now for the is empty, we're going to fill with hex C000. That's equivalent to negative hex 4000. Okay, remember that the base is 4000. The empty is going to be negative hex 4000. Okay, any question? Okay, so here, right, to visualize your random numbers, let's say we start with the value here, right? So this is your decimal equivalent, and then your hex equivalent to that, right? So here's the decimal, here's the hex. Okay, so if you can have 20 values. So when you sequence this, it's gonna see, we would start with seeding at 0. Now in the equation, we have to initialize a certain value so that way we can implement the randomization using the actual equation. Okay, so we would seed in this case, I'm sorry, we would seed at 1. So when you have the various seed, you can generate the seed as x is 0 or x is 1 and so on. And your scope is going to be between 1 and 32,767. Okay, so we just need to fill out our program, and you can take a look at the lab page for the code I posted there. So I'm going to go through it now. So we are going to start with origination address at hex 3000. Okay, we would start with loading A as because it is part of the equation. So A is going to get loaded to register 2. And M is going to get loaded to register 3. Okay, so I'm going to come back here and reference this for you real quick. So let's come back here. Okay, so we're working with this equation, but then we also have to set up this. Okay, so for your A of X, we need to make sure that we getting started to have mod M, and then we would put in these criteria or condition. Okay, so right there, because it's mod M, you are going to jump to subroutine. We have to do a division there. Okay, so where am I at on this part of the equation? Right here. Okay. And then now I have to move into here, and keep in mind that these variables, right, how I can represent Q and R is going to be M divided by A. And that's easy because we just have to set up our division subroutine and then reapply it. Okay. So now we're going to store our register 4 to Q, register 5 to R, right? And then we're going to load X to register 3 because we're in the loop. So for our loop section, we're going to load X to register 3. And we're going to load Q into register 2. Okay, let's come back here. So we have to get ready to do this part, right? The listing that they show here. And at one point, we're going to bring in the 7 so that way we can introduce the value so we can generate the random numbers. Okay. So okay. So once you load the variables, then you are going to jump to subroutine for the division. So now we want to have X divided by Q for the X mod Q. Okay. And X divided by Q for this part. Okay. Because now we want to do the if the value is greater or equal to 0, right? So we have to operate these. Okay. So here, what you have is you would have the division. So that way you can have X divided by Q. So once you have the division, you would return from that. Then you're going to store that value to X div Q. Okay, because we got to bring it back later. And then the same thing with X mod Q, because those are the things that are inside the parentheses, right? So once we have the result for this and this, we got to store it because we're going to bring it back down the line. You've seen this in the last lab. Okay, so here, that's what we have. Then we're going to load A to register 1. And we're going to take the X mod Q, we're going to load it to register 2. Okay. Then we're going to multiply. So coming back here, right? So I have to take A and multiply it by X mod Q as this part. So this is where I have to reload the A, and then I got to take what I store, right? Because I have to reuse it also. So that's why I store it. I want to take this and then bring it back so that way I can multiply here. Okay. So now what we have is then we have to jump to the subroutine mult. Okay. And so I try to put the comment so you can follow through. It's a little bit easier to track it. So then what I would do is I would take 0 and I would add it to register 3, which for the register 3, we previously have that as X, right? And then for our register 4, we want to put the result there. Okay, so basically it's a copy. Okay, so your R4 is going to have A times X mod Q. Okay. Because R3 is the X, and then we bring in the X mod Q, right? Then we're going to load X div Q, which we stored previously, to register 2. Okay, so now we're trying to work on this part right here, the second part. Okay, and keep in mind that R is going to be M mod A. Okay, and then we're trying to address this. So At this point, you have the div q. So you are going to now multiply that. So for your register 3, it's going to have R times X divided by Q. Then like what the lab has called for, we're going to do the 2's complement of register 3. And so after that, what we need to do is we need to bring it all together as an equation and put it on register 2. So as we had left off with register 3 and 4, those have the 2 larger pieces like the mod Q and the R times X divided by Q. So we're going to add those and put it on register 2. Now what we're going to do is we're going to check to see if it's greater or equal to 0 at register 2, because that's what, they said that if we have to see if it's greater or equal to 0. So if it is, then we're going to send it to skip. So here we're going to branch it because we're going to go greater or equal to 0. So we're going to branch 0 positive. Okay. Then now we're going to load M to register 1. Okay. And so for the next part, what we're going to do is we're going to take register 1, which is M. Okay. And your register 2, which previously you saw that this is the A times X mod Q and minus R times X divided by Q. So when you look at this, right, you have this piece already. We just check for positive and or equal to 0. Okay. Because we have to 2 complement because we have to do the negative R here, right? So now what we're going to do is we're going to add the M for the second part. Okay. So here we load the M and then we add the M for the second part. Okay. Because the second condition, we have to do a plus M. So that's why we do that here. Then we're going to store X to register 2 for the skip. Now we're going to start loading the stack. Okay, so first we're going to load the base address. You got to tell the system that this is the location where it's going to start the stack. So base is going to be hex 4000. We're going to load it at register 6. That's where it's going to begin, right? And as you move it up and down, when you push it, right? So that's going to change throughout, depending on the operation. So your base is loaded to R6. Then we're going to load X to register 3. Now we're going to begin our stack. So you have a stack label. So we're going to clear register 2. We're going to add 10 to register 2. Okay. So let's come back over here. Okay, so here, now we're going to do the division. So we're going to call for the division subroutine. We're going to put register 5 onto register 0. So basically we do a register copy here. So where did I leave off with register 5? If you follow it back up, right, you have the mod Q. And then we're going to push. Okay, so the stack is really designed for you to bring in the value, right? And then use that value to output. So, and as we using multiple digits, we gotta do 1 digit at a time and so on.
I have a quick question.
Yeah.
With this one, since we're pushing, is this the first digit that's going to be pushed into the hundreds value?
Yeah.
Off to the right?
Yeah. So,
okay.
So you're gonna push, you're gonna push the left first. Right? So when you come back over here, it shows you the example. Oh, down here. Right. So when I push, I'm going to push, I'm going to push the least significant first. And then when we output in reverse. So when we push it in, because 7 is going to be last, right? And output. So we got to put it last. I'm sorry. So I was right. The left one first. So in this example, 5 comes in first because it needs to show up last. Okay. So the hundreds or the thousand, it depends on how many value, because it can go to the 1,000. Okay. So for the 10, because we're mod 10, we have to set that up. And so that's why you see it. And so this is why the division occurs. So now we're going to put register 5 onto register 0, and we're going to push. Then we're going to copy again register 4 to register 3. We're going to check the stack. If it is positive, then we're going to come back here. Otherwise, it's going to go to unstack. Okay. And then when we go to unstack, we're going to check it again. So we're going to jump to a subroutine right there. Okay. So now in the next part for the unstack, so for the branch positive, if it's positive, right, we're going to stack. Why is that? Because if there's value still, right, I wanted to be able to keep using the stack. So now for the unstack, what we're going to do is we're going to jump to subroutine is empty, like what the listing showed us. Then after that, if it's positive, we're going to go to cont, which is just going to continue, keep going. Then we're going to jump to subroutine pop. So, and as it pops, we got to show, right? We got to display. So it's going to decode, and in decode, we have to ASCII convert. So I have 2 subroutine, right? One, we're going to call them one after the other because they have to be together, right? So pop and then decode and then out. So I want to display after I decode. Then I'm going to go ahead and come back to unstack. So branch unconditionally to unstack. In the continue section, we're going to load space to register 0, and we're going to fill space with 10. Okay. Then we're going to out. Then we're going to load LC to register 6. And then again, remember earlier you saw the example, we're going to move it up. So subtract 1. Since we load here, we're going to store on the next part. So we're going to store register 6 with LC. And then we're going to branch 0 positive back to loop. So if it is greater or equal to 0, it's going to come back to loop. And then it's going to halt. Okay. So for the fill, our space is going to be 10 up to 10 digits. We're going to fill X at decimal 100. A, they already told us that we have to put A as 7. Your M, they already gave us this value, so 32,767. Your Q, your R, and the other ones, we just use arbitrary fill locations, so we just put those as 0. And then the base, we talked about this, so your stack base is at hex 4000. Remember that these are decimal values. Those are the integers that they ask us to use. And then this is just, you can use hex 0, same with decimal 0. And then for the LC, that's going to be 20. That's your loop counter. And why is it 20? Because we're doing 20 random numbers. So for the multiplication, we clear register 3. So now we're going to define our subroutine. So clear register 3, we're going to set up a loop. So we're going to take R1, add it with R3 and put it on R3. And then we're going to count it down for the loop, branch back to M loop if it is positive. And then again, for our subroutine, that's why we use subroutine. We're going to return from our subroutine. In the division, you want to store the value because you deal with quotient and remainder. So we're going to store save 1 to register 2 and save 2 to register 3. Clear register 4. We're going to do the 2 complement of register 2. Okay. So the 2 complement is going to be for the sign, right? For the R6. Then we're going to do a division loop. So clear register 5. We're going to add 1 to register 4. And then we're going to copy register 3 into register 5. And then we're going to take register 2, add it with register 3, and put it on register 3. Okay. So now if it's 0 positive, we're going to keep looping. And then we're going to subtract 1 from register 4 and return. So for the countdown for the loop and then return. So for the save register, we can arbitrarily fill it with the 0. For the push, so here you saw this also in the lab, right? Description. So we're gonna subtract 1, move it up, store it to register 0, return. For the pop, we saw this also in our lecture, because we push, we store. So opposite for the pop, we load. So LDR, load it to register 0 from register 6. And since we move it up, now we gotta push it, we pop, so it's gonna go down. So it's gonna do a +1, return. For the empty, we're gonna load empty, or is empty, we're gonna load empty to register 0. We're gonna take register 6, which is our meter, add it with register 0 and put it on register 0 so we can check. If it's 0, it's gonna go to is. This is like the lab description. Then we're gonna add 0 to register 0 and put it on register 0 and return. Okay. So when there is something, right? So we're gonna clear register 0. Then we're gonna add 1 to register 6, and then we're gonna return. Okay, so that allows you to check whether the stack is empty or not. Okay, so if there is, then you have the 1, right? Or I'm sorry, 0 is not empty, and then 1 is empty. Okay, so then for empty, we have to fill it with the negative hex 4000 or C0000. And then we're going to decode. So because it is an ASCII, now I chose to use decimal, but if you want to use the hex 30 for that, that's fine. So this we've seen before. So all of this add up to be 48 in decimal. So you have to add 48 to convert it back to ASCII character. Then we want to return from decode so we can make it into ASCII, so we can out it. And earlier you saw decode was used for the display, and that will be the end. So after you do this, make sure you save it as a .asm and then assemble. Then once we assemble, we just simply use our simulator. I'm gonna reinitialize my machine here. This one's like so easy. It doesn't require any additional input. So you can just load the file and then you just run. And then you go to your console and there it is. Okay. Now, if I do it again, will it have the same output? You can find out. Okay. Any question? Now, can we elevate this program a little bit? Sure can, right? You know, in assembly, it's a little bit long. Well, it's a lot longer, but it's a little bit more manual in how you get things in output from what you return, because there are multiple digits. So when you look at your console, right, these, they just disappear on me, but let me rerun this. So yeah, so as you see it, right, you have multiple digits. And it did loop and it went through 20 times. So it puts each of the number there. But in order to get 700 like this, right, that came from the stack. So before it outputs 700, you gotta push it onto the stack and then check and then unstack it, right? And then output it. So that's how you get those numbers in there. Any question? So you do see that after you run, like for mine right here, you can see that it is because we fill that, right? So it did put that onto register 0 there. And so on. But registers, you know, it doesn't really hold permanent values anyway. So question. It seems when you first look at it, it might seem very complex, but ultimately it's not too bad. I think having the stack helps with thinking about like how the numbers go in and then how you can take each of the number and display it. So you are expected to use stack in all project options. So whichever option that you select, you have to implement stack. Now, if you choose not to implement stack, you just lose the points for that section. So I would use this reference, and also, you know, you have your notes. You've seen the example in the notes on how we can load it and then store it. Okay, so just very physically and think about like the physical in visualization of how your stack grow and shrink. And then, you know, if you are displaying multiple values like this, you can think about how each of the value gets stacked and unstacked. And remember last in, first out. So you push and you pop it. Okay. So doing this lab helps in thinking about how you would use the stack. Okay. Must you do it exactly like this? Not necessarily. You can implement it other ways. And this is the approach that we use because it addressed most of the things that they asked for in our lab exercise. Okay. But if you do look at other example online, for example, you know, you do see stack implementation and they might write it a little different. Okay. Question. All right. No question. Okay, so after this week, if you haven't gotten a team, I would suggest that like in the next week, figure out who you want to work with. It is not an option. Okay, if you submit your assignment as a one-person team, I don't know if I should grade it or not, right? In the past, like usually everybody gets into team, at least another person. I understand that team is difficult to work with sometimes, especially if you have a busy schedule. But I want you to be able to contribute and learn from one another. And in reality, you don't develop application by yourself. So you work with engineers and other developers ultimately. So down the line, you know, every school that you take for upper division, they're going to ask you to work with other people on your project. So we want to make sure that, you know, you're able to manage your project and a team. I'm available for questions. I just looked over a couple of the projects for CIS11 students. So if you want me to glance over, I will not troubleshoot your project for you. I will give you recommendation on where to go, or at least what area of your program to look at to fix if you're running into issues. But at this point, we should be able to at least, you know, write a functional program. Okay. And then if you have missing assignments, make sure that you get those to me by the end of the month. Before the final exam, I will have a lock date for everything. So except for the last few things that you need to submit. And so that way I can wrap up your grade. And for those of you who are graduating at the end of the semester, you know, your grade, you want your grades to be ready before you leave the college or the district. Any question? Nothing? Everybody okay with this? Okay, so let me stop recording.